On May 21, 2019, LIGO detected a gravitational wave that had crossed billions of light years to reach Earth. It should have looked familiar. Two black holes spiraling together, getting faster, louder, and finally merging. Instead, the signal was almost over before it began. GW 190521 was unusually short, and the waveform lacked a clearly identifiable inspiral, the part that normally tells us two black holes are closing in on each other. So here's the strange question. What if we weren't hearing a black hole merger happening here at all? What if we were hearing its aftermath after it crossed a wormhole from somewhere else? The conventional explanation is already extraordinary. LIGO and Virgo interpreted GW 190521 as the merger of black holes about 85 and 66 times the mass of our Sun, producing a roughly 142 solar mass remnant. The first clear gravitational wave detection of an intermediate mass black hole. But that creates another mystery. A normal merger has three acts: inspiral, merger, and ringdown. The inspiral is the rising chirp as the black holes orbit faster and closer. The merger is the peak. Then the newborn black hole settles down, ringing like a struck bell. GW 190521 mostly looks like that final burst. And that missing beginning is exactly where the story gets interesting. In 2025, physicists proposed a radical alternative. Perhaps the signal was a single gravitational wave echo from a black hole merger in another universe. In their model, the merger happened there, while part of its ring down traveled through a wormhole and emerged here. That sounds like science fiction. But wormholes are not forbidden by Einstein's equations. The problem is that the simplest Einstein-Rosen bridge isn't a usable tunnel. It collapses too quickly for anything to cross. A traversable wormhole requires something stranger. A way to keep its throat open against gravity, often represented by negative energy or other exotic physics. And now we hit the deeper mystery. What if wormholes aren't just strange tunnels in space-time? What if they are connected to the strangest phenomenon in quantum mechanics itself? Quantum entanglement links particles so strongly that measuring one is correlated with the other, even across enormous distances. It doesn't let us send ordinary information faster than light, but it does reveal a connection that classical physics struggles to describe intuitively. In 2013, Juan Maldacena and Leonard Susskind proposed the famous ER-EPR idea. Perhaps the geometry of an Einstein-Rosen bridge and the physics of quantum entanglement are two descriptions of the same underlying connection. If that sounds abstract, here's why physicists care. General relativity describes gravity and space-time. Quantum mechanics describes particles and information. Black holes are where those two theories collide and where our understanding of information becomes deeply uncomfortable. So the wormhole idea isn't just about traveling through space. It touches one of physics' biggest questions. How can information survive a black hole? And this is where the story gets even stranger. In 2022, researchers used Google's Sycamore quantum processor to simulate a simplified system with the mathematical behavior expected from a traversable holographic wormhole. They inserted quantum information into one side and observed the corresponding information emerge from the other. They did not create a physical tunnel through space-time, but they demonstrated something much more interesting than a sci-fi headline. A quantum system can reproduce dynamics that, through a holographic correspondence, are described as information traveling through a wormhole. That doesn't prove cosmic wormholes exist, but it gives the idea something science needs, a way to test the mathematics. Now return to GW 190521. The wormhole hypothesis makes a surprisingly specific prediction. If a black hole merger happened in another universe and only its ringdown crossed the wormhole, we could receive a short pulse without seeing the earlier in-spiral. That is exactly the odd feature that made GW 190521 so interesting. But there's a catch. The ordinary explanation still fits the data better. The 2025 Wormhole study found the standard binary black hole model is favored, even though the data do not completely eliminate the more exotic possibility. So, did we actually hear a signal from another universe? No, not based on the evidence we have. GW 10521 remains best explained as a black hole merger, but the wormhole hypothesis changes what the signal means as a scientific mystery. It turns one strange waveform into a test of ideas connecting gravity, quantum information, and space-time itself. And maybe that's the most fascinating part. The gravitational wave lasted only a fraction of a second. Yet inside that tiny ripple is a question that reaches far beyond the collision that created it. Is space-time really the fundamental structure of reality? Or could it be an emergent consequence of something deeper? We don't know. But every time LIGO catches another ripple from the dark, the universe gives us another chance to find out.